Alright, so this is our final video. We're going to be talking about tangent lines. So the tangent line to the graph of a function at a point a f of a is characterized by two properties. First, it passes through the point a f of a, and second, the slope of the tangent line is equal to the slope of f at a. Now, remember that the slope of f at a, that is also the derivative of f at a, and we denote it with f prime of a. In the picture here, the tangent line will look something like this. Now, recall the equation of a line passing through a point x0, y0 with a slope of m could be written in this so-called point slope form, where the equation is y minus y0 equals m times x minus x0, and you can add the y0 to the other side. So we're going to be doing some examples of finding equations of tangent lines, and so we're going to need to know this formula in order to do that. Now, one of the key properties of the tangent line, the main property of it, the most important property of it, is that the tangent line to the graph of f at a point is, in a certain sense, the best linear approximation of f around that point. So in the picture, the tangent line approximates our function f pretty closely near this point. Further away from the point, it's not a good approximation anymore, but it's a pretty good approximation near that point. And in a certain sense, one can say that the tangent line is the best linear approximation to the function at this point, meaning that no other line that passes through this point will approximate the function as well as the tangent line. So in a certain sense, that is true, all right? I won't go into much detail about in what sense that is true. That's maybe something that you will see in your calculus course. Now, for the remainder of the video, I will just work through a couple of examples of writing out equations of tangent lines. Of course, we should start with the parabola, f of x equals x squared. We've been making heavy use of this guy in our previous videos. What we saw in the last video is that at this point 1, 1, we actually already calculated the slope of the parabola at this point. We found that it was equal to 2. All right, so using the equation of a line, we can write out the equation of the tangent line. To the parabola. At this point 1, 1. All right, so 1, 1 is my x naught, y naught. And the slope was the derivative of f at x equals 1, which was 2. All right. Okay, let's do an example that will be just a little bit more involved. Let's do a new function this time. F of x equals the square root of x. And let's find the equation of the tangent line. At x equals 9, okay? Now it's not necessary, but I will just draw a quick graph of this function. At x equals 9, the y-coordinate f of 9 would be the square root of 9, which would be 3. So for the equation of the tangent line, we already have a point that it passes through. So we already have our y naught as well as our x naught. What we need to do is calculate the slope of the tangent line, and then we will be finished. So the slope of the tangent line is going to be the derivative at x equals 9. And to calculate the derivative, we had two formulas for it. I will use the limit as h approaches 0 formulation, just because I feel like it. So remember the formula, it was the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, since f of x was the square root of x, f of 9 plus h would be the square root of 9 plus h. F of 9 is the square root of 9, which is 3. It's all over h. Now this is giving us a 0 over 0 indeterminate form. So to get around that, I'm going to multiply numerator and denominator by the conjugate of the numerator. So when I multiply the numerator out, I'm going to get the square root of 9 plus h all squared. And that just gets rid of the square root. And then I'm going to have minus 3 squared, which is 9. And the denominator, we'll leave it as h times the square root of 9 plus h plus 3. At this point in the numerator, 9 minus 9, they'll cancel each other out. After the 9's cancel out, we can also cancel out these h's. That leaves us with the limit as h approaches 0 of 1 over the square root of 9 plus h plus 3. And now if we plug in h equals 0, we're going to get 1 over 6 as a final answer. So that tells us that the slope of the tangent line would be equal to 1/6. All right. And finally, I'm going to do just one more quick example. We're going to take a look at f of x equals the sine of x. So in the last video, we computed the slope of the sine function at the origin. So that would be f prime when x equals 0. And we found that the slope was equal to 1. We know that the tangent line to the sine function at this point, it passes through the point 0, 0 for x naught and y naught. And then, as we're noting, the slope of the tangent line should be equal to 1. So altogether, that really simplifies to just be y equals x. Now, at this point, I do want to go back to the idea of how the tangent line is a good linear approximation to your function near that point of tangent t, if you will. In this case, our function was the sine of x, and we're finding that the equation of the tangent line at x equals 0 is x. So these two should be approximately equal to each other. Some of you might have seen this approximation before. Sine of x is approximately equal to x when x is close to 0. This comes up in physics, for instance, in a couple of places. All right, I think I'll end the video at this point. So in the problem set, there are a couple of examples which are designed to give you guys a deeper dive into the idea of how the tangent line can be used as a linear approximation to your function. So I hope you guys will find those problems enlightening. And I guess that's it. So thanks for watching this video. Thanks for watching all of the videos, assuming that you have at this point. And I hope that you have enjoyed this adventure, and I hope that you've gotten something out of it. Okay? Thanks.